Hey everyone, and welcome to the first video on the series in number sense. And so we're going to start off by taking a broad approach, just sort of the basics, and looking at different types of numbers and classifying what those numbers are. And so we've got this sort of modified Venn diagram that we're going to use to compare and classify the different types of numbers before we actually dive in and start doing anything with those numbers. So we first want to put them in some classifications and give them names so that we have a better way to talk about it. So I want you to imagine that every number you've ever thought of lives kind of inside the whole thing. We'll call this entire box all of the real numbers. Now, inside of all of these real numbers, the first distinction that we can make, you'll see that's the difference between, say, this side over here and this side over here, is the distinction between rational numbers and irrational numbers. Now, rational, I want you to kind of think there, the root of that is this word ratio, and a ratio is just when we compare two numbers. And comparing two numbers, a ratio is often written in fraction form, which is nearly the definition of what a rational number is. A rational number is any number that can be a fraction. And an emphasis as well on the can be, even numbers like, let's say, 1, 2, 3, 4, what we would count with, the counting numbers, and they have their own name, and we'll get to that eventually. They also can be written as fractions, like 2 over 1, 12 over 1, even 2 could be written as 6 over 3, but then also other numbers that can be written as fractions, but not also written in another form, like 2/3, 3/4. Well, I guess technically those can be written in other forms. We'll get to that. Like another form there of 2/3 would be 0.66666. That 6 would actually repeat forever. Or 3/4 is also 0.75. So we have any number that can be written as a fraction. Those are the rational numbers. Now, the irrational numbers, numbers that cannot be written as a fraction. For example, one of the probably most popular irrational numbers is the number pi, often represented with the Greek letter pi. It's a number, it's going to sound a little counterintuitive here. It's a ratio that compares the circumference to the diameter of any circle. But that number is kind of mysterious in that its decimal never actually ends. 3.14 is just an estimation. If you're familiar with that number, it's actually 3.14, I think 62, keeps going on and on and on. The decimal, there's never any pattern that repeats, and there's never any place where that decimal actually ends. Another really popular irrational number is the square root of 2. It is 1.4 something, just kind of goes on forever and ever and ever. And so a definition that's often given to describe what an irrational number is, we have a decimal that never terminates. So that's when it stops, like 0.75. If I were to convert 3/4 into a decimal in kind of the classic way of dividing, 3 divided by 4, and if I were to do that with long division, it would look like this. Well, 4 doesn't go into 3, but I think if I think of it as 3.0, then I can actually do the long division here, because 4 will go into 37 times. That's 28. We have 2 left over there. Add another 0, bring it down. If you remember this algorithm for division, 4 goes into 25 times. That is exactly 20. And when we subtract, we get 0. So we have that 0.75 that we discussed. And then if I do 2/3, in the same way. 3 doesn't go into 2, but it does go into 26 times. That's 18 with 2 left over. If we add a 0, bring it down, 3 goes into 26 times. That's 18 with 2 left over. And hopefully you can see this pattern that would just keep happening. I'm going to keep getting this 3 goes into 26 times, which is 18. I subtract, I get 2, and then I add another 0, bring it down again, I get another 20. So that's just going to keep going, which is why that doesn't terminate, but it does repeat. So it is still a rational number, a decimal that never terminates or repeats. If I could, in theory, represent, let's take pi, the absolutely perfect circumference of a circle and the absolutely perfect diameter of a circle, and I plugged those two numbers into the long division algorithm, I would end up in a scenario where I never had a 0 remainder, so it never terminates, and I never would wind up in a place where something is going to turn into a cycle of repeating the same number over and over and over and over and over again. And so that's where the irrational numbers go. All of the rational numbers, if they're written as a fraction, we can divide them out and get a decimal that terminates or repeats. So that's what we mean in the difference between rational and irrational numbers. Moving into the next few areas of this sort of modified Venn diagram, we'll be able to go a little faster. So after rational numbers, we have integers. And so this takes, if you imagine a number line going from, like, say, we'll just do -6, -5, -4, -3, -2, -1, and then 0, 1, 2, 3, so on and so forth. All the rational numbers live in the space between, and on the numbers as well. But the rational numbers, the vast majority of them, live in all of the spaces between what we will call the integers. So the integers here are your numbers that don't have decimals or fractions. So all your positive and negative numbers and 0 that aren't decimals and fractions. So those are your integers. We're not looking at the space between. If we start looking at the space between, then we're talking about rational numbers as well. And then if we keep moving, we have whole numbers. And so whole numbers is going to exclude all of the negatives. So we're going to have like 0, 1, 2, 3, so on and so forth. So it's all of the integers except the negative numbers. And then when we get to the sort of smallest classification, these are what we call the natural numbers. And the only difference between natural numbers and whole numbers, and I'll highlight that, really make it clear for you, is 0. Because 0 is sort of a special number. You can't actually have 0 of something. 0 is the absence of something. In fact, 0 is one of the most recent accepted numbers in our number system. I'm talking, really only in the past few hundred years have mathematicians and society in general accepted 0 as a number, because 0 is the absence of a number. It's the absence of value. So we do have a classification as well that doesn't include 0, and that is the natural numbers. Okay, so that's a kind of a look at, as a whole, just classifying numbers. If you're kind of taking notes as you watch this, you might want to keep track of the vocabulary there. Again, we got the irrational and the rational numbers, integers, whole numbers, and the natural numbers. Okay, so what we're going to look at now, kind of all at once, it's sort of the same skill set to be able to do these things. We're going to talk about comparing and ordering numbers. Comparing and ordering numbers. And sort of the key to being able to do that, the big thing that you need to be able to do or to be able to understand, is the equality of numbers in different forms. If we understand equality of numbers in different forms, then we will have a much easier job determining proper ordering or being able to properly compare different numbers. So what do I mean by that? What do I mean by equality of numbers in different forms? We've already talked about that a little bit. Take the 3/4, for example. 3/4 is also 0.75. It's also 75%. It is also 6/8. It could also be 12/16. And this list could go on and on and on. There are lots of different ways to represent a value that is equivalent to all of these other values. So understanding equality, or really more accurately, equivalence of numbers in different forms. There's a subtle difference there between those two terms. So to get that correct, the equivalence of numbers in different forms. That's what we want to be able to really understand and to be able to do. And so, for example, if I had this scenario here, 3/8, and I wanted to compare that number to, let's say, 36%. And what do I mean by compare? Well, I just want to know which one's bigger. If I put them in order from least to greatest, which one comes first? If I was talking about a sale, which one would I rather have, right? If I want to know which number's bigger, or maybe I want to know which number's smaller, I just want to be able to accurately compare these two numbers. When they're in different forms, and by form, I mean here we have a fraction, and here we have a percent. When they're in different forms, they're a little more difficult to compare. Even if I can compare them, in my mind, I may be subconsciously doing some sort of conversion in my head to put them in the same form. So that's exactly what we want to be able to do. We want to understand, right? We want to understand equivalence of numbers in different forms, but with that understanding, what we're going to actually do is convert numbers into different forms. All right, so here's the basics of how we're going to do that. If we start with a fraction, we can turn this fraction into a decimal simply by understanding what a fraction is. And a fraction is just division. So if we divide, we can turn a fraction into a decimal. We actually already did that earlier. That's how I showed the idea of terminating and repeating decimals, was just by dividing. And you could do long division, right? 3 divided by 8. So, or 3/8 is 3 divided by 8, or using long division, 8 into 3. Or you could just grab a calculator and plug in on a calculator 3 divided by 8. And when you do that, you're going to get 0.375. Now, this is getting a little easier to compare, but maybe you're not real familiar with this comparison either. And a common misconception here might be, oh, well, 375 is bigger than 36. Well, yeah, that's true. And in this case, we would be okay because, in fact, 3/8 is greater than 36%. But sometimes that might get us in trouble. We could have a scenario like, let's say it was 40% and I had 0.375. Well, 375 is still bigger than 40, but 40% is bigger. And if we're not careful with place value, we can get into a little bit of trouble there. So let's also look at how we can convert a decimal to a percent. And the way that we're going to do that is just understanding what percent means. Percent, if we break that apart, percent just means out of, and cent means 100. So we're talking about something out of 100. I'm going to highlight that there so we can come back to it later, because we're going to use that definition again. So percent means out of 100. So we have this factor of 100. So converting between decimals and percents is just a matter of either multiplying or dividing by 100. And the easiest way to multiply or divide by factors of 10 is just moving the decimal around, because each place value represents a factor of 10. So 100, we need 2 factors of 10. So we're just going to move the decimal twice, 0.375. We'll move that decimal twice, 1, 2. It's now going to go here. So we have 37.5%. Now we can compare, instead of thinking of it as 3/8, 37.5% is greater than 36%. So once they are in the same form, it's a little easier to compare. Now we could also convert the other way if we needed to, a percent to a decimal. We would just do the reverse. So if I had 37.5%, I would just move the decimal the other direction. Now my decimal's here. Going from a decimal to a fraction, we're not just going to multiply. It's not quite as simple as just doing the opposite that we did, like we did with decimal percent to decimal. We want to think a little bit about place value. So if I have 0.375, I want to think about the place value that my last number is in, right? And how we would actually say this number. The accurate way wouldn't be 0.375, it would be 375. And then we look at that last place value. It's in the tenths, hundredths, thousandths, 375 thousandths. And this here, thousandths, is the clue that I need for how I write this as a fraction. I'm just going to write it as 375 over 1,000. Now, there is some simplifying that would have to be done here, a bit of reducing. But when it comes to reducing and simplifying and writing fractions in easier forms, I always recommend and teach, and even when I do this myself, I would rather do a few extra steps and not push myself and get potentially get confused or make mistakes. So just taking kind of bigger or smaller, rather easier steps is totally okay, totally acceptable. Like I know right away that both of these numbers are divisible by 5 because they both end in 5 or 0. So that's where I'm going to start. 1,000 divided by 5. Well, no, 100 divided by 5 is 20. So this is 200. And then 375 divided by 5. I could, a couple things in my head that I'm thinking here. I know 100 again is 20. So in the 300, I have 60 of them. And then 75 divided by 5 is 15. So we have 75. All right, just adding those two together. Now I'm going to do this again. Another time going by 5, it will be 40 and 15. I could go by 5 again and get 3 and 8. And well, there we go, 3/8, which is exactly what we started with, was the 3/8. Now, this brings up something that I want to point out, and thinking smarter, not harder. If the point of your converting is just to compare, meaning the answer to the question isn't the conversion itself, you're just using the conversion to help you. So the actual values you get are just helping you think and answer a different, larger question. Then it doesn't really matter which direction you convert. We could have converted 36% to a fraction, or we could have converted 3/8 to a percent. Either way would have put them in the same form and allowed me to make that comparison a little easier than when they were in different forms. So I would recommend that you pick the ones that are easier for you. And for me, that means I'm not gonna pick this route very often. If I can avoid converting things to fractions if conversion is not the purpose, like I don't need to know that it's 3/8 and my answer isn't 3/8, then I probably wouldn't have done this. That's why my first instinct here was to convert 3/8 to the percent, not the other way around. And it's not because I can't do it, not because I think it's difficult, but it's just more steps. Using a calculator, which I have on my phone all the time, on the general knowledge assessment, you have that 4-function calculator with you. We can do these other 3 processes much simpler. And doing that much simpler using that calculator is going to allow us, just for less work, which is going to lead to less mistakes and more saved time, which is really, really what we want. Good mathematicians are efficient, and they use the tools they have, and they pick the methods that get them to the answer in the best possible way. If I were going to order numbers, so that's just, comparing 2 numbers. Let's say I had a list of numbers like, let's say we'll take 3/8 and we'll use that 36%, but let's also throw in 0.37, and let's throw in 4/9, and let's throw in 5/8, and let's throw in 1/3. Right, so we're throwing a few extra numbers. We're sort of working through the same process. We're just doing it more times. So in order to put these, let's say we wanted to put them in order from least to greatest, I still need to be able to compare all of the numbers and figure out which ones are larger, which ones are smaller. And again, it leads me right back to this same thing. It's a lot easier to do if they're all in the same form. And because I have a decimal, and because I have some fractions that have different denominators, it's hard to compare fractions with different denominators. We need them really to have the same denominator or the same numerator if we want to compare them to each other. I think at least what I would choose in this situation would be just convert everything to decimals. Again, especially if I have a calculator handy, all I got to do is plug in 3 divided by 8, and I get that 0.375. Calculator does the work for me. Here, I'm just going to move the decimal twice. 0.36. This one's already decimal. 4/9. I'm just going to plug in on the calculator. 4 divided by 9, we get 0.44. 5/8, we'll do 5 divided by 8. We're going to get 0.625. And then 1/3, 1 divided by 3, we get 0.33. And then on these two, they actually repeat. So I'll put a line over them to notate that. All right, now that they are all decimals, we can compare them. Except if we're not careful, there is one other mistake that we could make that concerns place value. So some of these, the way the calculator gave it to me, has 3 places. Some of them have 2. And if we're not careful, we may think like, well, 375 is bigger than 44, right? But technically, 3 is 3/10, right? It's like having 3 dimes. A dime is a tenth of a dollar. And this 4 is 4/10. It's like having 4 dimes. Well, doesn't, the pennies aren't really concerned now because I already have, in this case, more dimes than I have dimes over here. So we also want to think about place value and really just look at the largest place value we have and only compare the smaller place values if we need to. Okay, so the smallest place value that I have in the 10th place, the smallest number, is 3. I have a few numbers with 3 in the 10th place. So these are all going to come before the one with the 4 in the 10th place and the 6 in the 10th place. So now I'm going to go look at the next place value. We have a 7, a 6, another 7, and a 3. Well, looking at the hundredths place, this right here is my smallest number. So 0.33 is my smallest number. That was the 1/3. So that's going to go first. All right. That's out of there. So now looking, the 6 is next. So 0.36, which was the 36%. So that's out of there. All right, now these two have the same, 3737. But if we look at the next place value, we have a 5 and we have nothing. So it's kind of like a 0 here. So this guy will be next, 0.37, which was in fact 0.37. That's the one that started a decimal. And then we have the 0.375, which is 3/8. Then the 4/4, which was the 4/9. And then the last number that we have is the 0.625. There's some commas in here. The 0.625, which was the 5/8. And so now we have these numbers listed in order from least to greatest. We could just flip that around, go from greatest to least, and order them that way to get that as well. So again, the idea here, the two big things, is understanding equivalence of different forms of numbers, and understanding that equivalence, being able to convert, because if we can convert our numbers into being the same form, and again, by form, we're talking about fractions, decimals, and percents. If we have all fractions, and again, fractions need either a common denominator or a common numerator to compare. If we have all decimals or we have all percents, then we can easily make those comparisons between the different types of numbers. So that wraps up this first video on number sense and being able to compare and order numbers.